Hello there, and welcome to Chapter 9 videos. These videos are all about molecular geometry. So in the last chapter we were looking at Lewis structures, actual bonding between atoms. In this chapter we're going to talk about how those atoms bonding affects what they look like in 3 dimensions. And so molecular geometry is what we're talking about when we're talking about the shapes of molecules in 3 dimensions. So this first bit on the actual shapes that I'm going to show you is all dependent upon this theory, which is called the valence shell electron pair repulsion. So that whenever you see this VESPR is how we say it, V-S-E-P-R, VESPR, think valence shell electron pair repulsion. So you know what the valence shell is. Those are the electrons that are in the outermost shell of the particular atoms. Electron, of course, are electrons. Pair, remember, electrons are paired in these molecules in the Lewis structure. So you see electron pairs, the ones not involved in bonding. And you also see the ones that are involved in bonding as lines, written as lines. And then repulsion, remember that electrons, they repel each other. So pairs of electrons, they actually end up being repelling each other. This is what governs the entire shape. This is what governs the molecular shape of all molecules, is this valence shell electron pair repulsion. These electrons are essentially trying to get as far away from each other as possible in 3-dimensional space. And so these geometries that we are about to look at are the way these electrons get as far away as possible. So let's look at some of the most basic electron geometries. And for this, I'm going to actually use some molecules that have those particular electron geometries so that you can see the Lewis structure and how the Lewis structure affects the shape of the molecule. So consider carbon dioxide and ozone. If you were to draw the Lewis structure for carbon dioxide, it would look like this. You'd put carbon in the center because it's the least electronegative element. You would need double bonds to each of the oxygens, and then you would have two lone pair electrons, or two pairs of electrons on the oxygens. So two sets of lone pair electrons on each oxygen. If you were to draw ozone, it would look like this, where you would have oxygen in the center, two oxygens bonded out to left and right, and then you would have one of those oxygens being doubly bonded, one single bond. You'd have one lone pair of electrons on the central oxygen, two on the oxygen with the double bond, three pairs of electrons, lone pair electrons on the oxygen with the single double bond, and two pairs, and three pairs of lone pair electrons on the oxygen with the single bond. So if we think about this, about the geometries or the shapes of the atoms around, or of the electrons around the central atom, okay, so this applies, these electron geometries only apply to atoms that are bonded to more than one thing. We would consider this one to have kind of a linear geometry where the electrons are on this side and then on this side of the carbon. They'd be to get as far away from each other as possible. They would be at an angle of 180 degrees and be in a plane. Down here, in order for these electrons in these bonded regions and unbonded regions to get as far away from each other as possible, you would need to have essentially, remember it goes around at 360 degrees, you'd need to have essentially 120 degree angles between the different electron domains. So if we look at, and notice that the number of electron domains, when we talk about electron domains around us, any atom, we're talking about all of the bonding domains. So notice that this is one electron domain, even though it has 4 electrons written there. Down here, this is one electron domain, this is one electron domain, and this is one electron domain around this central atom. So this has 3 electron domains. This has got 2 electron domains. And so in your textbook, you see that you have these large tables where it has electron domain geometries as a function of number of electron domains. So something with 2 electron domains, those domains are trying to get as far away from each other as possible. If there's something like in a double bond, they are stuck between, essentially sitting between these two nuclei, but they're trying to get as far away from each other, as far away from these electrons. These electrons are trying to get as far away from these electrons as possible, and with only two domains, that ends up in a linear shape. If you're looking at something with three domains, in a plane you have 120 degrees, right? So in one plane, to get as far away from each other as possible, you end up being 120 degrees apart. And so these are the shapes that you need to know. So this 180 is called linear. This 120 all the way around is called trigonal planar. It's in one plane, so it's not coming out of or going into the screen. One plane, and there are essentially three different things around it, or it's forming a triangle if you draw that shape there. Keep that in mind. Let's consider a few more electron geometries. If we check out the Lewis structures for PCl3, PCl5, and IF5, these are the Lewis structures that we would have if we wrote them correctly. Notice that there's a single a lone pair of electrons on this phosphorus here and a lone pair of electrons on this iodine here. And so the number of electron domains are 4, 5, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Okay, so that's the number of electron domains around the central atoms, the atoms that have more than one thing bonded to them. Again, going to that table in your textbook, if you have 4 electron domains, they arrange, it's not 4 in a plane anymore. Now the way to get as far apart as possible is you move out of that plane, start going into 3 dimensions. And this is the shape of that will be formed when these electron domains are getting as far away apart as possible. The bonding angle between all of these electron domains is, or not bonding angle, the angle between all these electron domains is 109.5. This particular shape is called tetrahedral. You'll need to know the names of these shapes and what they represent. Drawing them, don't have to I'll know how to draw them so much. But know that if you got 4 electron domains around an atom, you end up with a tetrahedral electron geometry for that. If you go to 5 electron domains, thing like PCl5, this is called a trigonal bipyramidal, where you have one of the electron domains up top, one of the electron domains down bottom, and then in a plane you have basically a trigonal planar arrangement for the electrons in the plane. So these 3 here, here, and here. These are all 120 apart, all the way in that plane, and then you got a 90-degree angle from electron domain to electron domain shown here, and again a 90-degree angle from here to here, or from here to here, or from this back guy down to here. Those are all at 90 degrees. And so those are the predicted, they say bond angles, but these are not necessarily bonds. And finally, for something with 6 electron domains around the central atom, that's called octahedral. It looks a lot like trigonal pyramidal, except in that plane, instead of having 3 electron domains, we now have 4. So if you have 4 things in a plane, so 4 divided by 160 is 90, right? Or 360 is 90. Then you also have these angles here, here and here, or here and here, or here and there. That's all 90 degrees, and then the angle down here, those are 90-degree angles. So the only angles available in the octahedral are 90-degree angles.